Hello, welcome back to CS 128 Honors. I apologize for my voice, I'm a bit sick. Today we'll be covering generic data types and a bit of smart pointers later. We, we will cover an example using smart pointers with generics on top. Today we'll have a lot of C++ analogs to deal with. So, in Rust, several types can contain other types, like collections, which can contain more primitive types such as ints, floats, or anything. A generic, labeled by this type T, represents an ambiguous type that is determined on compile time. Like, if you give it an integer, T will match integer. Yeah. So, here's an example here. Both functions here have the exact same function. They do the same things, except they have a different data type. What if instead of writing two functions, we wanted to write only one? That'd make it a lot easier, right? So instead of like declaring this type here, we could just declare a generic type. That generic, labeled T, is the generic type of anything here. Sorry. So you may be familiar with template in C++, where you can define a generic type for a class. In Rust, it works kind of similarly to where you can use it for the same features. Like earlier, we covered option T and result T. Result also is another generic error type, E. These letters don't really matter, they're just there to represent any arbitrary type. So in structs, you declare generics quite easily, just like this. For point T, you can have it either a point here, you can I32 or F32. It works the same way. It just will have the X and Y are the exact same type. Here, since you implicitly define it here, you don't even need to explicitly define the type, since it already gives you a 1 and a 2, which by default are 32-bit integers. So, you can also make a struct that accepts multiple generic types. TU. You don't have to label them TU. Like for example, in a hash map, it's KV. Just convention since key value pair. But the T and the U don't exactly stand for anything, but T is used because T stands for type, right? So when you give it two different ones here, T and U can be a different type, since they're not defined by the same generic. For every type you want to use in a function, you need to list them separately in the function signature or in the struct definition here. Since you want to use two different types, you need to list two different types here. And if you want to use the same type, you can just do I32, I32. In enums, it works pretty much the same way. The number t here, or sorry, not number t, but the variant containing the type t can be any type you want, like I32, U32. This is just an unsigned integer, so it can't be negative. But yeah, it works the same. You can even declare more types like this and use them completely separately, just like you did in the struct with x and y. But here, you don't even need to have any organization, but you need to pass in all of them in through the definition here, and then use all of them here. So, as I mentioned earlier, this is the option type you all know and love, and this is the result type. It's defined with the generic type T, to where it just says it wraps something of some type. And here it wraps it with an OK or an error. E is just used as a generic for the error types. So in methods, like this, for t specifically, you can implement here x to return the x value of this point. Notice how here we do implement t, and here we also do point t. This is important. And here, since we declare the t's here, we're allowed to use t inside of these in this brace. If you wanted to, you could implement a function for a specific type. Notice how here we just had t for a generic type. But if we want to work for distances, for integers, we can implement for I32 here only for I32. So it wouldn't work on, for example, an F64. Like here, no method was found. But for I32 it would be found since we implemented it for I32 specifically. In functions, you can do the same. Just like earlier, we had these two, and it seems wasteful to do two separate functions for the same purpose. So here, largest, you declare the generic type here, and then in the function declaration of the parameters, you can use the generic types you plug in. So, Rust is very good at implicitly determining what types you want to use. Like here, you pass it a vector of integers, and it knows you want to use integers. So you don't even have to handle all of this specifically. Though, sometimes a generic type might not implement the feature you want, since some types, like for example, could or could not be comparable. If you took 124, Java has a comparable class that is extended often that you need to, yeah, it has a comparable class. Rust, next lecture we'll talk about this more, but has something called a trait, which it's a different form of like inheritance that instead of inheriting from a class, you inherit certain traits. But like this, you want t such that t implements this partial ord. So partial ordering essentially. You want is this colon here limits t just to types or primitives that implement this comparison. So now, moving on to smart pointers. In C++, you've gotten used to using raw pointers, which are essentially just integers to locations in memory. These, however, can have problems. You'll have to deal with null pointers or dangling pointers, which Rust has a very smart way of managing, using smart pointers. For example, string and vector here manage their own memory, and they know the length of the collections, and they take ownership. Also, when smart pointers, like box or RC, go out of scope, the data is deleted for you. Unlike in C++, where if your pointer goes out of scope but you haven't deleted the data in memory, you have a memory leak, which means you're not freeing up all the memory you're using, so you will eventually run out of memory. Due to ownership rules, safe Rust does not allow raw pointers. I emphasize safe Rust because in Rust you technically can use raw pointers if you declare an unsafe block of code, but this is highly unadvised, and smart pointers are a much better way of handling this. So, the first smart pointer we'll cover is box. This is like a raw pointer with some extra features. Box can point to any data type as declared by this generic type t. It can even have like pointers to vectors or strings, anything really. And when this box is dropped, it goes out of scope, the data is deleted from the memory, and then the pointer is deleted too. So it always manages its memory on the heap. Essentially, it has a built-in destructor that you don't have to worry about. Boxes are the most easy to use in Rust. You just simply do box new, just like you do new in C++. But you do box new with the data you want inside. If you want to make it mutable, you can declare mut with mut to modify the stored data. Like let mut heap int equals box new 4. You can also dereference it, just like you would in C++. When calling functions on this data, Rust will handle it for you. So, what is the difference between a box and a reference? Before in this class, we've used references, which essentially point to other variables. Unlike a pointer, which in this case box owns, since the pointer box contains a pointer to this memory, but only box can access this memory. References borrow, they don't own it. And box, it doesn't have a null pointer, but using option, you can simply re-implement a null pointer, but much safer since it requires you to check for it every time, so you can't accidentally dereference null pointers. So, why boxes? One way is that some types require that you know the size at compile time, like an array, for example. This is why vectors store all their memory on the heap instead of the stack, since arrays on the stack must know their memory at compile time. Yeah, same with strings and vectors. They both allocate arrays on the heap, which lets you allocate any amount you want. So we'll cover an example, linked list. However, first let's see what not to do when covering a linked list. So you have a node here, link, that has your data of type T. We're just having T implement this display trait, which means that you can print it to the console. Then your next, you call to a link T, but option, because you might not have a next link. So you have none or another link. The problem with this though is now this link owns the next link. So Rust doesn't know the exact size of link. So technically, link could be of infinite size, which, since it's not known at compile time, is not allowed to be done on the stack, which is where it would be defined by default. So to correct this, we can wrap that link in a box, so the link is stored on the heap. This makes it so that the size on the stack is constant, since it's just a pointer, which are constant size. And then box, you can simply dereference to get the next option. And just like we mentioned earlier, option box is a way to get null pointer functionality without the danger of null pointers, since you have to manually check every time. Yeah, so thank you. This was a bit of a longer lecture, but some announcements. Homework 8 has been released. It is due a week from tomorrow at midnight. So March 7th. Today is February 27th. MP2 is due 2 weeks from tomorrow. And yeah, thank you for listening.